G'day everyone, day 7, variable capacitors. So capacitors at their most fundamental are just two pieces of metal separated by a dielectric or an insulator or vacuum or something that doesn't conduct basically. So what I have here is some cellulose acetate overhead transparency material which I've put some aluminium tape on, and I've hooked it up. I have two plates and I've hooked them up here to obviously the cellulose acetate is just an insulator so they don't short out, and it's kind of hard to hold floppy things at a set distance from each other. So I've hooked them up here to the capacitance meter, and as you can see the capacitance will vary as I overlap them, and will increase as the area between the plates increases. But also the distance. So capacitance is proportional to area and inversely proportional to the distance between the plates. So as I pull them apart, the capacitance drops. As I bring them together, the capacitance rises, and as I squeeze them together, capacitance goes up a lot. So you can get the best part of a nanofarad out of this kind of area if you squeeze them down nice and close together. So I was talking to someone about all the kind of projects that I might do for the Advent calendar. And obviously many radio projects, some of the simple ones like some of the ones we did last year, for example, many of the radio projects that we did used variable capacitors. Now, variable capacitors were once, these beautiful things of a bygone era that you could go and purchase or rip out of some antique mantle radio or something. Nowadays, not so available. Unfortunately, with modern technology, this kind of thing is just not used that much. I mean, this is beautiful. Look, it's got an anti-backlash system here. It's got a reduction drive. It's a fundamentally straight line frequency, a logarithmic capacitance capacitor. You can see that it's got the plates aren't circular. They're sort of this teardrop off-center rotated shape. It's also got a compression trimmer here for tracking adjustments. Yeah, no, you just can't get stuff like this anymore. If you can, it's ridiculously expensive. Whenever I go to a Hampfest, there's always someone selling capacitors, and I normally come home with a hoard of them. I have probably thousands now of various different sizes and shapes and particular technology. But yeah, I should probably put them up on eBay and stop hoarding them. I tend to be a bit of a hoarder, and I'll probably have now more than I'll ever use. Anyway, that's a story for a different time. A lot of AM radios still use these polyvericon capacitors, which are actually a pretty cool piece of technology. I think it was a Japanese firm that first worked out how to make these things cheaply, and made the small AM radios of the 70s and 80s as practical as they were, and as cheap as they were. So inside there's a bunch of little thin aluminium plates separated by I think it's polyethylene on these. It might not be polyethylene, because sometimes they seem to be quite lossy. Now, I don't know if that's their physical construction, if these... Probably, yeah, it might even be just the quality of the metal. I don't know, but they do tend to be lossy, and I've measured Qs on these guys on the order of less than 200, which for a capacitor is just astonishingly bad. Anyway, these are still fairly widely available, though they are reasonably expensive. I mean, you can be up to $5 for one of these guys, which just seems crazy to me. Also, obviously, trimmers of various shapes and sizes. They're built much the same. These things tend to have reasonably high Q, probably because they use more copper in the construction. They're just physically smaller. These things work at right up to VHF quite happily. These are examples of this is a butterfly capacitor. So it has two separate floating, the stator parts, and the rotor is shared between them. Typically with a variable capacitor, this part you'll ground and arrange the circuit such that you can ground the rotor, so touch capacitance won't affect this. And these sides will then be referenced to ground with a variable capacitance. Similar to a butterfly capacitor, we also have a differential capacitor which can be useful. So as the capacitance on one side decreases, it increases on the other. Also, I've seen ones that were designed for before they could make phase lock loops or varicap diodes. They actually used to have a motor spinning a cap to do sweep generators, which was, I've seen some that have very free bearings and one that even had a motor attached to it. This is a compression trimmer. Compression trimmers have layers of metal and mica normally, or some other insulator. and as you screw down this screw in the middle, it pulls the layers together. So they have a very non-linear capacitance with angular change of the screw, but they're normally used for trimmers, and once set, they're just left at that value. You can get them quite large. I've seen ones that are like 2 inches square, and they can be very high voltage, so they can be quite useful. They can normally have very good Q as well. Depends on their construction, the material that they're made out of, but some high power transmitters, particularly high power VHF transmitters, use quite large trimmers of this kind. This is one of my personal favourites. I don't make these anymore. They're called Beehive Trimmers. I haven't seen one available anywhere other than the surplus market for at least 10 years. They've got a very thickly anodized aluminium shell, and they're constructed like an old-fashioned beehive. You can see in there they've got like this concentric cylindrical arrangement, and the disc is a conductor, and there's this special contact up in here. They're actually a beautiful piece of engineering. They were quite common in radios, but again, bygone era, you can't really get them anymore. I like them for the fact that they've got a wide range of variability, so you can... this is a 70 picofarad capacitor, for example, and it goes from basically 2 or 3 picofarads there all the way down to 70. It's got lots of turns. I've seen one chap that made an LCR bridge that actually used this, and he calibrated it by scribing lines on it, and he had like a micrometer style adjustment for capacitance in the bridge balance, which I thought was a really cool idea. Physically, it's a bit like a piston trimmer. You can get piston trimmers that are like just 2 tubes that slide on each other. There's a lot of homebrew capacitors out there that work on the same principle, but I think the nesting is really cool. It puts a lot of variable capacitance in a fairly small area. Voltage obviously is a bit limited because everything's quite close together, and this oxide layer is only so thick because there's nothing that really holds it from getting... I've seen quite a few that are dead short when I've bought them because someone scratched them or hit them with a screwdriver and dented them, and then they're scraping, and that doesn't it doesn't take long before that completely destroys them. So in my discussions here with people about what to do for advent calendar projects, we were talking about variable capacitors, and again, they just can't get them anymore, or they're very hard to get, particularly in some parts of the world. So I thought I'd come up with some kind of alternative. Obviously, you can build a capacitor like this out of circuit board. It's a lot of work, but it's certainly relatively easy to do, particularly one that's circularly symmetric. So it's just a bunch of half circles. It's pretty easy to lay out in a CAD program and cut it out on a mill, or even just with tin snips, but a lot of work. So I took this principle to its natural conclusion, right? So instead of sliding, which is a bit mechanically complicated, I decided to roll them up. So as you roll them up, they come into more intimate contact. And the end result was this thing. So it's a bit of a contraption, but I made an acrylic box, and you can see there's 2 plates, and the plates start off far apart, and as you rotate it, they get pulled into closer and closer contact. It's not particularly linear, but it sort of has the right kind of properties. Right out here, the capacitance is very small, and it changes quite slowly, which is good for tuning at high frequencies. And as you come in here, the capacitance rises very quickly, which is again what you want for tuning at low frequencies. So it does have some interesting properties. This particular acrylic shell could obviously be made out of something else. You might want to put a plate here to remove touch capacitance, so minimize your body capacitance as you try and manipulate it. It does have a little bit of drift. Like when you tighten it up, I've only just used Kapton tape here to hold in place. What would be better would be to have some kind of clamp that clamps this such that when it's wound right up, the tension can't pull on the tape and change the geometry. Again, I threw this together pretty quickly. Most of the time was actually spent designing the model for laser cutting, but the actual construction of it went together pretty quick once I had the bits and pieces. For designing it, I used OpenSCAD, which is my favourite thing for doing 2.5D kind of CAD. So these I ended up not using. They were just to locate the ends of the shaft here so they didn't move. I ended up using this pour-on foam to implement kind of like a bearing, friction bearing, which is not optimal, But it's super simple, and it definitely works. Well, I think what we'll have to do is build something with this. It's about 10 to 150 to 200 picofarads, somewhere around there. Let's put it on the meter. Okay. You can see there, if I tune down capacitance, that's about the minimum there, about 10 or 11 picofarads. So it doesn't rise particularly quickly. You see there is that little bit of, also it's obviously my body here is, because there's no shielding, I'm just touching the leads and I'm going to upset the capacitance measurements. This isn't really a fair test. The real test of stability is obviously to build an oscillator with it and listen to it, and I would have done that tonight, but I just ran out of time. We might do that in a later. Well, definitely if we build a receiver with it, I'll find out all about how good or bad its stability is. So keep tightening it. And you can get up to about 100 and almost 200 picofarads. So the interesting thing is, while I was building it, I actually had the strips much longer. I had them, the full sheet of cellulose acetate, which by the way is a terrible dielectric and you shouldn't use for this purpose. But anyway, and I could build a capacitor like this that varied from a couple hundred picofarads to more than 3 nanofarads, which is just amazing. If you want to make a long wave receiver or some kind of low frequency variable capacitor, it's actually pretty interesting. I've never thought about making a variable capacitor so large, because certainly a variable capacitor with a high voltage rating could be manufactured just like this, or could be hand assembled like this, and it would be much cheaper and much physically smaller than one built like this, if you could even get them. Particularly for antenna tuners, if you did do that, you'd want to replace the dielectric material in here with something that has a much better loss tangent. I think the loss tangent of cellulose acetate is about 200 or 300 times 10 to the minus 4. I think it's on the order of the same as polyvinyl chloride, and we know PVC is terrible dielectric. A quick, easy way to test if a dielectric is any good is just to stick it in the microwave and microwave it on high for a couple of seconds and see if it gets warm. Polystyrene will fail that test quite spectacularly, whereas something like polypropylene or polyethylene or Teflon will barely get warm or won't get warm at all. That's obviously a test at 2.5 gigahertz as opposed to a test down at lower frequencies. And some materials are oddly good at one end of the frequency spectrum or the other. It all depends on their internal construction. So ionic plastics like PVC have a lot of ionic polarity to them, because they've got these big chlorine molecules hanging off the sides of the chains, and they've got an elastic kind of electrostatic polar, because all the electrons are kind of pulled away by the negative charge. Anyway, pushed away by the negative charge. But anyway, very polar plastics don't do particularly well for dielectrics, and they have high loss. But whereas a non-polar plastic that's more wax-like, like a polyethylene, normally have pretty low loss tangents. Anyway, this is not a discussion about dielectric materials, but you can find the tables online. There's a lot of information out there. Quartz and materials like that are spectacular. Teflon is obviously really good. But the commonly available materials that you can get in sheet form, it's definitely polyethylene and polypropylene, both of which you can get in large sheets for construction material. You can get them in 6mm sheets or 4mm sheets. They're normally pretty expensive to buy, because you have to buy like a 24-inch wide minimum kind of sheet and 150 feet of it. But you can also get sheet protectors, like small A4 or letter-sized envelopes that you can put pieces of paper in. Such things are quite useful for exactly this kind of purpose, where you want to insulate something. They're also particularly handy for manufacturing high voltage capacitors that you might want to use for a Tesla coil. Polypropylene is probably your best bet there, because it has a good dielectric breakdown and a good loss tangent. Alrighty, so super simple to make. If you happen to have some this aluminium tape, which is cheap as, I used Kapton. Doesn't have to be Kapton, it could just as easily be any random cellophane tape or whatever. The acrylic is probably going to be the hardest part. You could make it entirely out of cardboard if you wanted to. There's nothing to stop you. Oh, I don't know why this thing doesn't just turn itself off instead of beep at me. It's super annoying. I'll put this file up online. I'll link it for anyone that might want to construct it themselves. You could obviously make this out of cardboard or out of timber or out of whatever. I'll put the OpenSCAD source up there as well, so if the material thickness is different, I use this tab T-slot system, and the easiest way to control, I've got parameters for the thickness of these, so for the material thickness is part of the algorithm for calculating the geometry of this, so it's pretty easy if you have a different thickness material or you have a different axial size. You can obviously use a very small axle and wind up more of the material more rapidly. There's a whole bunch of stuff that you can play around with there. It's good stuff to experiment with. I'm not completely sure myself what would be the optimum. I'd have to think about that. I haven't done the math. But if you want to make a crystal set where you manufacture the capacitor yourself, this is definitely, it looks like a pretty promising way to do it. Particularly if you want to make a long wave crystal set, which I've never tried. Alrighty, I think that's enough for today, and tomorrow's a weekend, so we might get a more complicated project in tomorrow. Alrighty, till then, bye.